In the next two examples, we want to see how the shear force and bending moment diagrams will look like when we apply a rectangular load with a magnitude of 2 kN per meter over the entire length of our beam, which is 6 meters. Again, we start solving the problem by drawing the free body diagram of the beam. So, if this is our beam, this is point A, this is point B, this is our load. We have AY, AX, BY, and the length of our beam is 6 meters. The second step is writing the equations of equilibrium and determining the support reactions. So, now, before writing the equations of equilibrium, we have to substitute this distributed load with a single resultant concentrated load, which is applied at the centroid of this rectangle, or right in the middle. So, this will be how our new free body diagram will look like. The magnitude of our single resultant force is equal to the area under our distributed load, or 2 multiplied by 6, or 12 kilonewton, which is applied at the centroid of this rectangle, or in the middle, which is located at a distance 3 meters from each end. Now, in the x direction, if we write sigma of x equal to 0, this direction, we only have ax. So, ax is equal to 0. In the y direction, we have ay minus 12 plus by is equal to 0. So, ay plus by is equal to 12. If we write sigma m around any point along the beam, for example, point A, in this direction, we have 12 multiplied by 3 minus by multiplied by 6 equal to 0. And this will give us the by equal to 6 kilonewton. And if we put by in this equation, we have ay plus 6 equal to 12. So ay is also equal to 6 kilonewton. And this will be our free body diagram with the two support reactions we determined. And now I'm going to show you how you can draw the shear force and bending moment diagrams for this simply supported beam using the graphical method. All right. At point A, we have an upward or positive concentrated load with a magnitude of 6 kilonewton. So in our shear diagram, we're going to have an upward jump. So this is positive 6. From point A to point B, we don't have any concentrated loads applied. So using the first principle, we can say that the change in shear between these 2 points will be equal to the area under our distributed load. So delta V between A and B is equal to, or negative 2, since the distributed load is acting downward, negative 2 multiplied by this distance, or 6 meters, or negative 12 kilonewton. VA is positive 6. So VB will be equal to VA plus delta V AB, or positive 6 minus 12, or negative 6 kilonewton. So this is our shear at point B, which is equal to negative 6. Now, using the second principle, we know the slope of our shear diagram at any point between these 2 points where we have a distributed load applied and we don't have any concentrated loads applied in between, is equal to the intensity of our distributed load at that point. And since the intensity of our distributed load is constant, equal to -2, because it's acting downward, the slope of our shear diagram at any point between A and B will also be equal to -2. So we can draw a straight line between these 2 points. And the slope of this line is -12 divided by 6, or -2, which is equal to this intensity. And finally, at point B, we have an upward concentrated load with a magnitude of +6. So we're going to have an upward jump at point B. -6 plus +6 will bring us back to shear force equal to 0. So this is how our shear diagram will look like. Now, by looking at this shear diagram, we can see that right in the middle of the beam, the shear force is equal to 0. So at a distance 3 meters from each end, the shear force is equal to 0. But in general, or when we have a more complicated distributed load, in order to determine at what point the shear force will be equal to 0, we can use the method of section. So let's say we don't know at what point the shear force will become equal to 0. We cut the beam at a distance x. And we assume that at this distance x, the shear force is equal to 0. I'm going to copy this beam, paste it here. We're analyzing the left cut segment, so the positive shear force is downward, positive moment is counterclockwise. Now, in the y direction, we have 6 kilonewton here, minus this resultant force, which has a magnitude of 2 multiplied by x, or 2x, minus 2x, minus Vx is equal to 0. So Vx is equal to 6 minus 2x. And we know that at this point x, the shear force is equal to 0. So Vx is equal to 0. And 6 minus 2x will be equal to 0, which gives you an x equal to 3, which is the same as this value that we could guess by looking at our shear diagram. Now, using our shear diagram, we're going to draw our moment diagram. At point A, we don't have any concentrated moments, so we're not going to have a jump in our moment diagram. And this will be our MA. From point A to B, we know our shear diagram intersects with our x-axis at x equal to 3. We're in the middle of the beam, and between these 2 points, we don't have any concentrated moments applied. So the change in moment between these 2 points will be equal to the area under our shear diagram between them, or this area. And this area is equal to +6 multiplied by 3 divided by 2, or +9. So MA is equal to 0. Change in shear between A and C is +9. So MC will be equal to 0 plus 9, or +9 kilonewton meter, or somewhere here. This is +9. Now, using the fourth principle, we know the slope of our moment diagram at any point between these 2 points will be equal to the intensity of our shear at that point. And we can see that the intensity of our shear is decreasing from +6 to 0. So the slope is not constant, unlike the previous examples that we solved, and we can't draw a straight line to connect these 2 points. And we have to connect these 2 points using a curved line. So it should either be a curved diagram like this, or this. Now, we know the intensity of our shear is decreasing between these 2 points. So the slope of our moment diagram also needs to decrease. In this curve, you can see that the slope is increasing, but in this one here, the slope of the curve is decreasing. So these two lines cannot represent our moment diagram, and our moment diagram should look something like this. I'm going to remove these, change the color. Now, from this point C to point B, again, we don't have any concentrated moments applied. So the change in moment between these 2 points will be the area under our shear diagram, or this area here, which is equal to -6 multiplied by 3 divided by 2, or -9. MC was equal to +9. The change in shear between C and B is -9. So +9 plus -9 will give you an MB equal to 0. Now, we have to connect these 2 points together. We know the slope of our moment diagram at any point in between will be equal to the intensity of our shear at that point. And the magnitude of our shear is increasing from 0 to 6. So the slope of our moment diagram will change from 0 to -6. Again, we know this intensity is not constant, so we won't be able to draw a straight line and connect these 2 points like what we did in the previous examples, but we have to draw either a curve like this or something like this. Now, again, the magnitude of our shear is increasing, so the slope of our moment diagram has to increase. In this curve, we can see that the slope is decreasing and these lines are becoming shallower, while we are looking for a curve which has an increasing slope, or the slope of these lines are becoming steeper. So these 2 diagrams cannot represent our moment diagram, and we can remove them. I'm going to change the color of this line, and this will be how your moment diagram will look like. We have positive slopes which are decreasing to a point where the slope is equal to 0, and that's exactly where our shear was equal to 0. And then from that point, the magnitude of our shear increases again, so our moment diagram will have steeper slopes, and you can see that the maximum magnitude of moment happens exactly where the shear force was equal to 0. So these are your shear force and bending moment diagrams for a simply supported beam where you have a downward rectangular distributed load applied over the entire length of the beam. The distributed load is downward, so the shear will decrease. And if we make this distributed load upward, we're going to get opposite support reactions. Our shear diagram will be increasing, and the moment diagram will look something like this. We have a downward concentrated load, so downward jump. The change in shear between these 2 points will be the area under the distributed load, or 2 multiplied by 6, or 12. -6 plus 12 will bring you to shear force equal to +6. The slope of shear diagram between these 2 points will be equal to the intensity of our distributed load at that point. The intensity is constantly equal to +2, so the slope of shear diagram will also be equal to +2, and we can draw a straight line. So this is your shear diagram. At point A, we don't have any concentrated moments applied. So we don't have any jump in the moment diagram at point A. So MA is equal to 0. The change in moment between point A and C will be equal to the area under our shear diagram, where -6 multiplied by 3 divided by 2, or -9. MA was equal to 0. Delta MAC is equal to -9, so MC will be equal to -9. The slope of moment diagram at any point in between will be equal to the intensity of shear at that point. The intensity of shear in the beginning was -6, and at the end was equal to 0. So it's not constant, and we can't connect these 2 points using a straight line. We have to draw a curved line. Now, we can't draw a curve like this because we know the magnitude of our shear is decreasing from 6 to 0. So our moment diagram will have to have shallower slopes from A to C, but here we can see that it's becoming steeper, while in this graph it's becoming shallower. So this is how the moment diagram will look like between A and C. And from C to B, the magnitude of the shear is increasing from 0 to 6. So the slope of the moment diagram will have to become steeper. We can't draw a straight line again. We need a curve. So this is not going to work. We either have to draw a curve like this or a curve like this. In the upper curve, the slope is decreasing, while we know the intensity of the shear is increasing, so the slope of the moment diagram also has to increase. So these two diagrams cannot represent our moment diagram. And this is how the moment diagram will look like between points C and B. And now in the next 4 examples, we're going to see how the shear force and bending moment diagrams will look like when we have different types of triangular loads applied to our beam.